The equations which describe fluid flow are written in terms of derivatives. For example, here's the equation which describes conservation of mass. To actually make use of them, we need to do some integration. With the finite volume method, this means integrating with respect to both time and volume. In this form, computers can't help us, since calculating these integrals exactly is either impossible or extremely time-consuming. So we have to make some approximations to get the equations into a simpler form. For example, to get rid of the first integral, we usually approximate density to be constant everywhere within a given cell. This is part of the second-order finite volume method, which most CFD packages use. The fvSchemes file contains all the numerical approximations to be used. By the end of this video, you'll know what fvSchemes settings to use for 95% of the sims you'll run. I've added timestamps in the description, so feel free to skip around the video. On screen right now are a few recommended prerequisites for this video. These are linked in the description. With that out of the way, let's begin. Typically there's a trade-off between how accurate a scheme is and how stable it is. The goal is to use the most accurate scheme possible without introducing random oscillations and instability. For example, all the plots on screen right now were generated from identical cases. The only difference between them is the choice of divergence scheme. ddtSchemes contains methods to approximate the integrals of time derivatives. In the cavity case, we have this setting. Default means this approximation is used for every time derivative, and Euler refers to the first-order backwards Euler time integration method. Here's a ranking of options from most stable to least stable. As mentioned before, the most stable option is the least accurate, and vice versa. As a side note, steady state just sets all the time derivatives to 0, so solvers which rely on a time derivative will not work properly with steady state. A good rule of thumb is to start with Crank-Nicolson 0.9, then drop to Euler if necessary, or try backward if the sim is stable. gradSchemes contains methods to approximate the gradient integrals. In the cavity case we have this setting. Default again means the approximation is used for every gradient. Gauss refers to the green Gauss gradient scheme, which requires an interpolation scheme, in this case linear interpolation. Grad P is the gradient of pressure, but it has the same setting as the default, so this line is useless. If we change the gradient scheme to something else, for example least squares, then the grad P setting would override the default setting. These are the most common options. For extra stability, you can add a limiter. There are other limiters, but seldom delimited is usually okay. divSchemes contains methods to approximate the divergence integrals. Default none forces us to specify the scheme to be used for each divergence separately. If we forget to specify one of the required schemes, OpenFOAM will crash and print the missing divergence scheme. Div phi u refers to the integral of divergence of phi times u, where u is the velocity and phi is the flux, which, for solvers using incompressible fluids, is equal to the velocity. This corresponds to the advection term. Gauss refers to the Gauss divergence theorem, which converts volume integrals of divergence into surface integrals of the original variable. To work out these surface integrals, we need to know the value of the variable at the surface, so an interpolation scheme is needed, in this case linear. The divergence terms are critical to the stability and accuracy of a CFD sim, which is why each scheme is specified separately. Here are some common divergence schemes. If you're running a steady-state simulation, use the bounded keyword. This adds an extra term into the equation which aids convergence but doesn't affect the final result. Overall, use Gauss-limited linear 1.0 for most fields, Gauss-limited linear v 1.0 for vector fields, and Gauss linear for the viscosity scheme, which you'll recognize as the one with the really long name. snGradSchemes contains methods of approximating the dot product of a gradient of a variable and the surface normal vector. If the gradient and the surface normal are aligned, then the calculation is simple. However, if there is some difference, called non-orthogonality, then we need to make a correction. In this case, CheckMesh reports 0 degrees of non-orthogonality, so the orthogonal scheme is used. These are the most common alternative options. The choice depends on your maximum mesh non-orthogonality angle. For non-orthogonality above 70, you'll also need additional non-orthogonal correctors in your fvSolution file. I'll go over this in a separate video, but for now just visit the links in the description for more information. LaplacianSchemes contains methods to approximate the Laplacian integrals. Gauss again refers to the Gauss divergence theorem, so we'll end up with a surface integral of a dot product of a gradient and a surface normal vector. So we need two things, an interpolation scheme and a surface normal gradient scheme. In this case, linear is the interpolation scheme and orthogonal is the surface normal gradient scheme. The setting I almost always use is Gauss linear, followed by whatever is in snGradSchemes. Finally, interpolationSchemes contains methods to find the value of a variable at a face, given the values at the cell centroids on either side of that face. In this case, linear is the interpolation scheme. I've personally never needed any other interpolation scheme for my simulations. I've skipped over many of the more unusual settings for the sake of time, but the settings in this video should have you covered for the vast majority of simpler simulations. Please see the links in the description for more information, or check the OpenFOAM documentation for further details. This marks the end of this video. Please leave any questions in the comments, and thanks for watching.